It is easy to take the universe we live in for granted. The earth we live on, the stars in the sky, and the thousands of mysteries that lie out there in the deep black void. For hundreds of years, astronomers have been studying what lies beyond the planet we live on. In those years, we have come up with many models, explanations, and predictions. However, despite all this, there is still so much left that we don't know. Time is one of the most fundamental concepts that surrounds our existence. It is, however, not as simple as we expect it to be. Most of us believe time to be something that flows, like a river. But like a river, anything that flows must be relative to something. In the case of a river, it flows relative to the river bank. So, what does time flow relative to? Keeping in mind the answer could be nothing, and the way our brain comprehends time is just wrong.
So before Einstein, there was kind of a question about whether space and time, we should think of them as intrinsically like relational in the sense that is that they're telling you, how far away things are from each other in space and time, and whether it's kind of those relationships of distance and of duration that kind of constitute space and time, or whether it was better to think of space and time as like backdrops. So if space and time are like backdrops, then it's like you have a stage, right? And the stage is just there, and you have space, and you have time. You have a timeline that's just there, and then everything's happening. Physics is happening. In front of that backdrop or on that stage. And so those are kind of two different ways to think about space and time. And there was a big debate back in the 18th century between Leibniz and Clarke, who was kind of a disciple of Isaac Newton, kind of arguing about those two different views of space and time. And what Einstein kind of figured out, and this has been shown to be correct, is that space and time are not backdrops. So we shouldn't think of space and time as absolute realities that exist prior to matter, to stuff. But rather that they're always relative to one another and to matter. So, for instance, one consequence of that is that there's no such thing as, for example, universal simultaneity. So if I observe two things happening at the same time, another observer who's traveling at a speed relative to me won't see those things happening at the same time. So that means that time is something local. And Einstein always thought about this, kind of the trope is rods and clocks. So you have a rod, and that's how you define what a distance is, and you have a clock, and that defines what time is. But those are things that you have locally, and someone else elsewhere will have a rod and a clock. But if you try and compare your rod and your clock to his, you need to do certain calculations before your rods and your clocks will tell you the same thing. And you can do those calculations, but the point is that you can't expect your clock to run at the same speed as my clock all the time, or your rod to be the same length as my rod. Lengths and durations are always locally defined. And if you want to translate between different locations in space or time, you need to do the proper calculation.
To explain this idea of time in space, Einstein came up with the theory of relativity, the world famous E equals mc squared, which basically said that mass and energy are the same physical entity and can be interchangeable.
Yeah, it's really interesting topic that you've asked. It can get really complicated, but also there's actually a really simple way to explain it. Um, in that, if you think of space as just, you know, being like a place, right? And then time, you're quite familiar with it. I don't think Einstein's theory of relativity drastically changes what you should think of one of the other as. But basically, that theory of relativity just says that the two are related. Um, you know, and they are related quite intricately, but you don't quite see. It's not obvious how related they are or how directly related they are until you get to quite extremes. In particular, you start thinking about moving close to the speed of light, and you'll see the speed of light kind of come up a lot in many areas of physics, but especially when you talk about the theory of relativity. So kind of you start seeing weird things that you don't expect when we start thinking about things traveling close to the speed of light. In that clocks don't when you try to measure time, clocks don't behave quite as well, quite the same as we expect them to. Some a clock moving very fast will appear to move tick slower than we expect it to, for example. And if you imagine a rocket ship moving really, really fast, that actually causes it to kind of squish down and along the direction of its travel. So that really just comes out of a lot of math relating, the geometry of space and saying that time is just another, just one similar dimension, similar to like one of the directions of space. So it's kind of all that is really. I'm sure that like is not quite what you know. It's not enough to explain the entire theory of relativity, but yeah, that's kind of the beginner's concept of what that is and what it means.
Similar to time, there are many mysteries in the universe that we are yet to solve. In my opinion, dark energy is perhaps one of the biggest of these mysteries. What's scarier than the name is how little we know about this phenomenon. The term dark is just a cloud term for everything we can't explain about the expansion of our universe.
So we have observations in the recent universe that show that galaxies are receding away from each other at a rate that's faster in the present than it was in the past. And this is counter to what you would assume if you just assumed an expanding universe. The universe can be expanding, but that acceleration is unexplained by any of our models that existed before these observations. And so people needed to add in some terms, some kind of extra components of the universe to try to explain that acceleration. And generally, those terms or models are just referred to as dark energy. What does that mean? Basically, the dark term here sort of just refers to the unknown, or it can refer to the fact that whatever this energy is, it's not emitting any kind of light. We can't see it in any kind of a traditional way. We only infer it by the motions that we see in our present day universe, and also by the way that early universe observations relate to sort of what we predict for present day. So given all of that, there's a huge landscape of sort of options that you can put in for something that causes this acceleration, but currently none of them fit the data very well. None of them are very well constrained, and none of them have a very strong sort of theoretical backing. And typically what we do is we try to make a sort of phenomenological model, which means that you create a theory that describes this energy that changes in some way over time, or maybe it even changes in space, and you can tweak that and play around with it in different ways, and you can try to then place constraints or try to kind of measure whether that is happening with real data. But those models are not very well sort of motivated theoretically. So the big problem is that I think we don't really have a strong theory that suggests that there's naturally any kind of we call it field or even like background quantity that should cause this kind of acceleration that behaves so strangely compared to everything else in our universe.
It's interesting that you asked about dark energy and also the theory of relativity, because I'm sure you might have learned this already, but the two topics are actually quite interconnected. In that Einstein's theory of relativity, the first part of it is what I just explained to you, which relates to concepts of space and time as being similar things. They're not quite exactly the same, but they're quite similar. And if you work through the combination of geometry of space and also include time as another dimension, it kind of drops out that just from the math itself that you can just recreate gravity with just geometry, basically. And kind of the second things that are then related in the theory of relativity are the concepts of mass and then and gravity. So you might hear sometimes that Einstein's theory of relativity is a theory of gravity, and that's what basically general relativity is. So the thing I described relating space and time, that's usually referred to as the theory of special relativity. But if you generalize it, you get something called the theory of general relativity. And these are just basically, a set of theories that kind of describe gravity. And the way it works is that, things that have mass, so like matter, us, can bend space and time, basically. And then the motions of those things follow kind of the shape and geometry of that space and time. So when Einstein wrote out those equations for the first time, he kind of added this extra part to his equations called what we call the cosmological constant. And the reason he added that actually is because he thought the universe was supposed to be static. He lived in a time where we thought the universe was eternal and just happened to be as it was always and always will be like this. So, the way he wrote his equations down, he needed this extra constant basically in his equations to make sure that things stayed the same. It turned out later that we make observations of space and we find things moving away from us as we look farther and farther away. So that tells us that space is actually expanding over time. So the universe is not static. So that actually happened. It's funny because he wrote these equations and he added this thing to make sure that the universe was static, and then it turns out we didn't need this constant. So it turned out he made these equations, he thought we needed this extra thing, and then we saw that his assumption that the universe was static was not true, so it dropped it. So we didn't need the constant anymore. And then later on, we made more observations and we found that space is currently expanding faster than it was before. So, we thought that this expansion of space was always happening. If we look far enough back, it turns out it wasn't moving as fast as it does now back then. So we go back to those equations and it turns out we actually do need something like that cosmological constant, just in a different way. And that's what dark energy is. It's just this extra thing to add into Einstein's equations to describe the universe and how we see it in terms of, how space works and how gravity works.
I think the way you introduced it was actually really good. I think you said something like it's a cloud term for something we don't understand. And that's very apt. So I often will say that dark energy is a name for our ignorance. So what do we know? We know that the universe is accelerating in its expansion. And we know that gravity does the opposite. Gravity meaning the attraction between massive between mass and mass energies causes the universe to slow down. So the universe is speeding up. We know that from empirical measurements. We also know from observations of the cosmic microwave background in the very early universe that there has to be this component. And so, but then kind of the question is, well, what is it? And the reason I like the way you described it is that if you think about like an algebra problem where you have like, 3x equals 52 or something, right? So you put an x in because you know there's a value there, but you don't know what it is, and you need to solve the equation to find it. Kind of similar thing with dark energy. We know that there's something. We know that the phenomenon exists, but we know there's an x, but we don't know what x is. And we know some of its properties. We know that it has a negative pressure, meaning it has this outward push, or this push that causes the universe to accelerate. We have kind of some constraints on how big that push is. We know that it's a property of the whole universe. So we know that on very small scales, where very small means like the solar system or even the galaxy, it's not an important factor. So it's kind of a universe-wide thing. We know that it has something to do with gravity, because it's dealing with the expansion of the whole universe. So we know a whole bunch of kind of things about this phenomenon, but exactly what it is what we're still trying to figure out. Yeah.
Right. This then begs the question, if dark energy is something we cannot see, how do we even begin to observe it scientifically?
Yeah, so the observations that we use, that we have used so far to sort of confirm the existence of some kind of dark energy or confirm the existence of cosmic acceleration, is the motions of galaxies, in particular the motions of distant galaxies. So you can measure their velocity, and that velocity is always receding from us. As soon as you go past a certain distance, everything is receding from us. And you can also measure their distances by various techniques. And that tends to be the harder part. Measuring distances in the universe is really difficult. And one of the ways that we can, well, there's many ways that have been proposed, and luckily now they're with multiple ways to measure distances. That helps sort of give confidence to the ways that have been used so far. But the classic way to do it is something called the distance ladder, where you figure out how to calibrate measurements to things that are close by. And then you use that calibration to then make measurements for things that are further and further and further. So you use different techniques at different distances to ultimately figure out the distance to galaxies that are quite far away from us. And ultimately, in distant galaxies, we tend to use observations of a certain kind of supernovae, type 1a supernovae. And so in terms of future observations, basically, if you have those measurements in the relatively late time universe, in other words, the universe that's relatively close to us, still large scales, but representing sort of the latest times in our universe. That tells you right now how fast the universe is expanding. And you go farther, and then you can start to get the measurements of how fast it was expanding in the past. And that gives you the measurements of acceleration. So those were the advancements in the 90s that showed us that things are accelerating. And then the further and further you're able to go into, in terms of distance from us, the further you're looking into the past, and you're able to start mapping out that expansion rate well into the universe's past. And if we can do that, we can measure not only whether this acceleration exists, but whether it's changing in time, and perhaps also we can measure, acceleration in one direction versus another, and see if it's changing at all in space. And we can try to sort of simulate different versions of universes with computers and see how things would look in different models, and then compare that to the data. And basically, the further that we can go into the past, the more data we have to compare, and the more constraints we have on the history of dark energy. So the upcoming advancements in telescopes like the Rubin Observatory, for example, and the Dark Energy Spectroscopic Instrument, DESI, these types of instruments are mapping our universe further and further into the past, and they're measuring these distances better and better, further into the past, and that's going to be able to help us understand which theories are viable and which are not. Whereas current observations are only sampling sort of the more recent universe and don't give us enough information on that.
Well, the way it was discovered in the late 1990s was by looking at distant supernovae. So when a supernova explodes, they all explode in very similar ways, so that they all explode with the same intrinsic brightness. But as you know, the further away something is, even if it's the same brightness, it gets dimmer as it gets further away, and it goes as r squared. And so you can use the brightness of supernova to figure out how far away they are. And then the universe is expanding, right? And so there's an expectation about the relationship between how fast they're moving away from us and how far away they are. That's what Hubble's law is, right? Things that are further away are moving away from us at faster velocities, but that exact relationship depends on how the universe is expanding. So in the late 90s, and people were trying to measure, well, how fast is the universe expanding? And so they were measuring these supernovae at different distances, and it didn't fit the expectation for how the universe should be expanding. And the only thing that could explain it is that the universe is speeding up in its expansion. That was the only thing that could explain why they were the dimness they were, compared to how fast they're moving away from us. And that's a really strong piece of evidence for dark energy, and one that's kind of has been borne out by subsequent observations of supernova. And then you can also look at the very early universe and do a very similar thing. So if you look at the cosmic microwave background, which is released soon after the Big Bang, you can look at the properties of the CMB, and you can do a very similar thing where you kind of you try and match up your expectation about how far away that is to how the universe is expanding. And similarly with the supernova, you find that that you really need this dark energy for your whole picture to fit together. And when you include dark energy, the theory works really, really well.
For those of you who don't know what CMB is, don't worry, I have you covered.
So CMB stands for the cosmic microwave background. It's called microwave because it's not in visible wavelengths. It's in microwave light, which is a little bit shorter wavelength than radio. It's called background because it's everywhere. So if you look, no matter where you look out in the sky, you see the same radiation, the same microwave radiation. So it's not like stars, which are like little points of light. This is light that's coming from everywhere on the sky with kind of equal intensity. And then it's called cosmic because it's filling the whole universe. And really, when it was discovered in the mid-60s, it was kind of like the final piece of evidence that convinced people in the Big Bang theory, because the only way to explain its existence is if the universe was once much smaller and hotter. And basically what we're seeing in the microwave background is the glow of the universe when it was small and hot. And we're seeing, and that light has been traveling for the whole age of the universe. So like for 14 billion years, it's just been traveling through empty space, and then it hits our telescopes. And we're seeing, because light travels at a finite speed, we're looking back in time. And when we look at this microwave background, we're seeing the universe as it was about 400,000 years after the Big Bang, which is an instant compared to the 14 billion year total age.
Yeah, observationally, we I don't know that we can directly know what it is, but we know that there is something here that behaves like that the thing that Einstein put in his equations originally. and its effect is that it will, cause the expansion of space to change over time. So we know that that changes over time because we can look out into the universe and we see faraway galaxies and they're moving away from us, and they're not moving away at the same rate. It depends how far away they are. And the farther away they are, the faster they should be moving. But if you look far enough away, that's not quite true anymore. They do still, the rate at which they're moving away from us is still faster, but not as fast as we expect. So that tells us that the space is expanding fast or speeding up over time. What exactly is causing it? I don't know if we can observe it directly because it's not like anything that we expect to know, right? We live on Earth and we're used to, how things operate on Earth. And these are effects that operate on scales of like galaxies and groups of galaxies. So it's really quite hard to wrap our heads around, observationally at least. Theoretically, we have these equations and we understand how gravity works. So we have somewhere to work from to, kind of tell us what it should be. And the reason it's dark energy is, this constant, this part of Einstein's equations that, describes the dark energy. When we write equations in physics, we care a lot about the units, units like, distance, time, things like that. And if you look at the units to make these equations make sense, the thing that, that component of the cosmological constant, it takes on what we call an energy density. So that's how much energy there is per volume of space, right? I don't know how a good way to describe that personally is, but density in general is like, you can think of, how much stuff there is in a given amount of space. So a rock is very dense. The air around you is not very dense, for example. It's kind of like that, but, an energy. And the way it works out these units is this thing kind of describes what we call an energy density kind of that describes it's an energy density related to kind of the amount of space there is, which is quite a difficult concept to wrap your head around, even if you have a physics degree. But at least we kind of have that to go from. And yeah, so, something like, an energy density related to, kind of space itself is quite a difficult concept to even wrap your head around, much less start looking for a way to, find what it is and, directly observe it. I don't even know where to begin for that.
Another such phenomenon is dark matter. Many people, including me, when first hear about dark matter and dark energy, assume them to be related. Though they share the word dark, both are independent of each other. So what is dark matter and how is it different from dark energy?
Let's start with what's the same. They both have the word dark, and in both cases that's a reference to our ignorance. In one sense. So dark matter is still something we don't have a handle on. On the other hand, the reason it's called dark matter is because we don't see it. So it doesn't interact with light, it doesn't glow, it doesn't block light. So actually, I was listening to a talk recently, and the person was saying, actually, we should think of it as transparent matter because it doesn't interact with light. If there were a whole bunch of dark matter between me and you, we wouldn't see it because the light would just pass right through it. So it doesn't interact with light, it doesn't glow. But the way we know that it's there is through its gravity. So for instance, there are many places we see this in the universe, but just to give one example, if you have a group of galaxies called the galaxy cluster, which typically have something like 50 galaxies, and because the galaxies are big and they've got a lot of mass, so they're all orbiting around each other. So you have this cluster of galaxies, all of the galaxies are orbiting around each other. And you look at how fast the galaxies are moving, and the speed that something orbits depends on the mass that it's orbiting around. And you find, if you look at how fast they're orbiting, you look at the shape of their orbits, you find that the mass of the galaxies alone can't possibly explain their orbits. There has to be a lot more mass there than we see just in the galaxies. And there are other examples of that, where you look at something and you see how it's moving, and you realize, wow, the gravity is just way too strong to make it move like that. There has to be more mass that we're not seeing, and hence dark matter, because it's dark because we don't see it, and it's matter because it's ponderous, it's massive, and it's creating this huge gravitational effect. And in fact, we wouldn't be here if it weren't for dark matter, because for structure to form in the universe, for like galaxies to collapse and start forming stars, really dark matter is a really important part of that equation. It gives us enough gravity so that we get structures like galaxies forming, in the amount of time that have passed since the beginning of the universe. So it actually plays a pretty important role in the makeup of the universe, even if we don't know what it is. And so to get back to the ignorance, like, we know there's something massive everywhere, but we don't know, is it a kind of particle? And if it is a kind of particle, how heavy is the particle? Is it lots of really light particles, or is it fewer heavy particles? Do those particles interact with each other? Do they maybe sometimes very rarely interact with regular matter? So there are experiments that are looking to detect dark matter particles, because maybe like 99.99999% of the time, dark matter just passes right through regular matter, but maybe 0.000001% of the time there'll be an interaction, and if so, maybe we could detect that.
There are two very different things. Dark matter is the term that we apply to the unknown or sort of an invisible form of matter that is causing a lot of weird gravitational effects in various parts of the universe. So, for example, one of the ways that we know that there's some extra matter that we can't see in the universe is that galaxies sort of rotate faster than they would if we only had regular matter that we can see that makes light or interacts with light. Another way is that by observations of clusters of galaxies, groups of hundreds to thousands of galaxies. They also have motions that are different than what you would predict if they were only coming from the light that we can see. And so dark matter interacts just like normal matter does in terms of gravity. The difference is just that it doesn't seem to interact in any way with electromagnetism in the way that normal matter does. Stars shine, gas emits some kind of light. We even emit light as humans. We emit sort of faint infrared light. And dark matter doesn't seem to emit or reflect or have any interactions with light. So that's different from dark energy. The way that it's different is basically the way that it interacts with the sort of fabric of space and time itself. Every component of the universe does cause curvature in space-time, but the way that dark matter causes curvature and affects the acceleration of, or affects the expansion of the universe is different than the way that dark energy does. And they also seem to have very different values. Dark energy seems to currently make up about 70% of the energy budget of the universe. Dark matter seems to make up about 20, 25, or 30%. Well, matter in total makes up about 30%. Dark matter makes up about 25%. So they behave differently in terms of how they affect the expansion of the universe. And they also make up very different amounts of our current universe. And in terms of the different ways they behave, that mostly comes down to the way that their density relates to their pressure. In general relativity, pressure is sort of, density and pressure behave a bit weirdly in a way that's maybe not so intuitive if you're more familiar with sort of typical, tabletop physics experiments where you talk about density and pressure. But in a nutshell, there's this very weird thing where dark energy has negative pressure. I won't go into that in a ton of detail, but basically that's sort of the reason that it's causing the accelerated expansion, whereas dark matter has pressure in the normal way.
That's a really good question. So, dark energy and dark matter share the same word dark. And the reason we call them dark is because we don't know what it is. That's literally all the dark means. So together they kind of make up what we call the dark sector of the universe. So there's just this stuff in the universe that we don't know what it is, but they cause these phenomena that we can observe. So for example, I just described dark energy as causing this expansion of space to, kind of accelerate over time. So it serves to push everything apart faster and faster over time. Dark matter is kind of not quite this operates at not quite the same level. It's the fact that we know matter has mass, right? And we also know that mass produces gravity. Okay. So we know, so if we look out and we see the sun, we know that it has a certain mass because there's a giant ball of gas that's very bright, and we know that it's very massive because it exerts gravity on us and allows us to orbit it. But if you look at large enough scales, say scales at the order of galaxies, we can count how many stars make up a galaxy, how much gas we think exists in a galaxy. And then we see how the stars orbit a galaxy. So a galaxy is a group of stars. And we see that these stars move very fast around a galaxy. And, it doesn't quite make sense when you consider how much mass that we can see in a galaxy actually exists, or how much mass we can observe in a galaxy, which either tells us that, somehow gravity is stronger at the scales of at galactic scales, or there's extra matter that is there but we can't see, with light. And there's been a lot of debate about which one is true. I don't think because it's kind of hard to tell, right? Like either gravity is somehow stronger at very large scales, or there's just some stuff we don't see. But the evidence seems to point towards the other thing, that there seems to be some kinds extra mass that we're not seeing. So we call this dark matter. So it's stuff that has mass but doesn't interact with light. So that's kind of one of the only probes we have of observing things in space is we just see light that it's emitted. So if it doesn't interact with light, then it can't emit or absorb light, but it's there and it has mass, so it produces gravity. So that's what dark matter is. It's just this extra stuff that we see that causes gravity because we can see the effects of its gravity, but we can't see it directly.
So, knowing all this, how far are we still from an answer?
It depends what you mean by an answer. Because for any physical phenomenon, you can always ask more questions, right? So for instance, we know, we didn't know 100 years ago that things were made out of atoms. We know now that things are made out of atoms. We know a lot about atoms. We know that they have nuclei and electrons, and that there's a strong force holding the nucleus together, and an electromagnetic force that keeps the electron in its orbital, and all these things. But we still have lots more questions about atoms, even though we know these things. I think it'll be the same thing with dark energy. Is that we'll learn more and more about it, but there'll always be more questions. I don't think this is going to be like a stopping point where we go, now we completely understand dark energy. But I think I just described what we do know about dark energy. Like we know kind of the basic properties. We know what it does. And what can we hope to learn in the near future? Well, one thing I think we can do better at, quite concretely, is measure like more precisely what its strength is. So exactly how fast is the universe expanding? And there are various measurements we can do to do that. So for instance, one observatory that I'm involved in, called HIRAX, its goal is to make a more precise measurement of how fast the universe has been expanding over the last few billion years. And if you can do that, then you can put stronger constraints on the equation that governs dark energy. So right now, one popular idea for dark energy is that it's a cosmological constant. Well, what's that? If you look at the theory of gravity that Einstein came up with in 1915, it very naturally has in it a constant of integration, if you know a little bit of calculus. And that constant has the properties that would give us dark energy. But if we can make a more precise measurement of how how fast the universe is accelerating, it could be that we either remain consistent with a cosmological constant, or it could be that we make a measurement that's in tension or even inconsistent with a cosmological constant, in which case it would be another type of physics, it would be another type of physical field. So I mean, that's something that in the coming years, hopefully, the kind of measurement we'll be able to make, that will tell us a lot about the nature of dark energy and exactly what physical thing causes it. The other, but then, as I said earlier, there are always more questions. So if it's a cosmological constant, there's still puzzles. So one puzzle is, why is it the size it is? Because it's actually quite small. Like, as I said, it doesn't affect us here in the solar system or even in the galaxy. So it's quite a small effect, but it's quite a small kind of push, but a big enough push that it's having a huge influence now over the whole universe. But so the question is, like, why is it so small, relative to what it could be? Because if you just make a very kind of straightforward prediction of how big it should be, knowing the physics we know, it should be like a 1 followed by 120 zeros, like that big of a number, bigger than it is. So like, why is it not 0, and why isn't that big? Why is it this tiny non-zero number? Is kind of another question. And I don't know if we have any good way currently of answering that question, but it is a question that people are thinking about.
Yeah, so I think the answer to that kind of depends on what you're satisfied with as a theory. So we do have a theory that fits very well right now that's called lambda. And lambda is the cosmological constant term. It's a term that you can put into Einstein's equations that invoke general relativity to describe the evolution and expansion of the universe. And if you put that in and you give it a certain value, that actually fits the observations very well. And in the last 20-25 years since dark energy was sort of discovered, we've had more and more and more data that keeps kind of confirming that this model fits very well. So in that way, you could say we're getting closer and closer to sort of confirming that lambda is correct, which in my opinion would be kind of boring because it's just a constant. It's constant in space, it's constant in time, and it's not a very exciting model. But then you can ask the question, well, what is lambda? If we also have the other kind of terms that come into these equations are, the energy density of matter. Matter is something that we can describe really well. We know how protons and electrons behave, and we can even break that down. Protons we can break down into quarks. So we have really strong, like, fundamental theories of what these things are, even down to the field level of quantum field theory. Whereas what that fundamental physics predicts in terms of a potential kind of constant background energy, which is what lambda would have to be, that prediction is really incorrect. That prediction doesn't work at all for what we measure. And people often talk about that prediction is 120 orders of magnitude off from the actual measured value. So sometimes people talk about it as the worst prediction in like theoretical physics or particle physics, because that is so wrong. But really, the reason that that's so wrong, as I understand it, is that we don't have a really connection between gravity and quantum mechanics on tiny scales. And so that theory is bound to be wrong because we don't actually know how that works. So in terms of getting, to answer your question, in terms of constraining options for a dark energy term that would change in time or change in space, we're getting closer and closer, and upcoming data in the next 10 or 20 years is going to really answer that question down to a pretty precise amount. But then if the answer is just lambda works and lambda is right, getting from knowing that to knowing what actually does that mean in terms of sort of the particle physics or quantum physics perspective, I think we're very far away from that. And
Right.
I think that for that we need a huge breakthrough. And some people are working on those kind of theories, but as far as I understand it, we haven't had a breakthrough.
Right.